Welcome to Lecture 9, in which we will discuss entangled 2-qubit and multiple qubit states, and also the measurement of 1 qubit of a 2-qubit state. And this material is all in Chapter 3 of your text. So let's start with entangled 2-qubit states. Now, as I hope you have seen from your book, this is really an easy idea. So let's jump right into it. For instance, in your book, it states that the four states of the four Bell states are all entangled. Now, let's write this way. The statement that the four Bell states are entangled means that each of them is incapable of being expressed as A0 plus B1, and take the tensor product of that with C0 plus D1. And let's check for a couple of cases. Well, let's check perhaps Phi plus. Now that is equal to 1 over square root of 2, 0, 0, plus 1, 1. And we're going to try to express it now as A0 plus B1 tensor product with C0 plus D1. Well, if we do that, then we see that this would give us AC 0, 0 plus AD 0, 1 plus BC 1, 0 plus BD 1, 1. Now, when we compare what we have on the right-hand side of this equation with what we have on the left, we see that AC must equal 1 over square root of 2. AD must be equal to 0. BC must be equal to 0. And BD must be equal to 1 over square root of 2. And we're arriving at that result simply by comparing the like terms. So the coefficient of 0, 0 up here is 1 over square root of 2. So the same thing must be true down here. And that's how we get AC is 1 over square root of 2. The coefficient of 0, 1 down here is AD, but there's no 0, 1 term up here, so AD must be 0. Likewise for BC. And then the coefficient of 1, 1 is BD. Coefficient of 1, 1 up here is 1 over square root of 2. So this is how we get these four equations. Now, if you look at the equation, this equation that AD is equal to 0, well, there's only two ways that can be true. Either A is 0 or D is equal to 0. But if A is equal to 0, then the first equation here couldn't possibly be true, because 0 times C would be 0, but A times C must be 1 over square root of 2. So that eliminates the possibility that A is equal to 0, so we'll cross that out. And now we must conclude that D is equal to 0, but D is equal to 0 contradicts the last equation, BD is equal to 1 over square root of 2. So this shows that this it is impossible to express phi plus in this way. So phi plus is said to be entangled. And in later sections, we will understand why entanglement is important. Now, just to do another example, to make sure that this is clear, let's look at problem 3.5 in your book. And in that one, you were asked, is the state one over square root of 2 times 0 plus 1 minus entangled? Now, the easy way to do this problem is the following. I will express 1 over square root of 2 0 plus 1 minus as in the following way, or I'll try to express it as A times 0 plus B times 1 tensor product with C times plus D times minus. Now, you might object to this, because up here when we were doing this example, in order to show that phi plus was entangled, we showed that it was impossible to express it as A times 0 plus B times 1 tensor product with C times 0 plus D times 1. But here we have C times plus D times minus. But remember what your book said about this being basis independent. When we talk about something being entangled or not, it does not matter what bases you use. Now, some are more convenient than others, and I'm suspecting that it will be convenient to use this basis for the second bit of this 2-qubit state, and this basis for the first bit of the 2-qubit state, simply because That's the way the state is expressed. The first qubit, the first bit of the the first qubit of the 2-qubit state is expressed in 0, 1, and the second qubit of the 2-qubit state is expressed in terms of plus minus. So I think that this will be the best way to do it, but I'll also show you how it would go if we went with our first attempt, just to show you that either way we come to the same conclusion. So let's see what happens here. Okay, when we write this out on the right hand side, we would get AC times 0 plus AD times 0 minus plus BC times 1 plus BD times 1 minus. And now if we do as we did before and compare to what we have on the left hand side, we see that this would require that AC is 1 over square root of 2. AD must be 0. BC must be 0. And finally, BD must be 1 over square root of 2. And we can see immediately that this is impossible, because if AC is 1 over square root of 2, then that means definitely A is not 0. Now, if AD is equal to 0 and A is not 0, then D must be 0. But if D is 0, then it would be impossible for BD to be 1 over square root of 2. So we say impossible, and therefore this state is entangled. And actually, I think rather than doing it myself, I think I'll leave it to you to try this for yourselves using C0 plus D1 for this second term. And I now, of course, well, maybe I had better do that myself just to make sure you see how to do that. So if we so this is entangled. But now, if you had stuck with the natural or the standard basis for both qubits of this 2-qubit state, let's see how that would have gone. So you'd have 1 over square root of 2 times 0 plus 1 minus is equal to A 0 plus B 1 tensor product with C 0 plus D 1. And so you would get on the right hand side AC 0 0. Maybe we had better maybe a quicker way would be just to do the following. So we'll have A0 plus B1 tensor product with C times plus minus plus d times plus minus minus. Let's see. Let's think about this. Maybe we need to let's check this. I believe we need a factor of square root of 2 in here, so let's check. Recall, let's just do a little scratch over here on the side. Plus is 1 over square root of 2, 0, plus 1 over square root of 2, 1, and minus is 1 over square root of 2, 0, minus 1 over square root of 2, 1. So if we add those together and multiply by square root of 2, we will get 0. So we need, instead of c here, we need c times the square root of 2. And likewise, if we take the plus vector minus the minus vector, we would get well, let's see, we need again d times the square root of 2. Nope, sorry. This should be over square root of 2 in each case. Okay, so c over square root of 2, and this should be d over the square root of 2. Because if you, let's just make sure this is clear. If we add these together, you see that the second terms drop out, and we get 1 over square root of 2, 0, plus 1 over square root of 2, 0, which is 2 over square root of 2, or square root of 2 times 0, which implies that the 0 vector is 1 over square root of 2 times plus minus. And if we, instead of adding those two lines, instead of adding these two lines here, if we subtracted them, we would get that the 1 ket is equal to 1 over square root of 2 times plus minus. And then when we take these two equations here and substitute for the 0 and the 1 here, using those equations, then this is what we get. Okay. So now that we've gotten that clear, we see that when we expand this, we would get AC over the square root of 2 0 plus AC over the square root of 2 0 minus plus AD over the square root of 2 0 plus minus AD not sure how I did that. Let's see if I can undo it now. Okay. So we had AD over square root of 2, 0 plus minus AD over square root of 2, 0 minus plus BC over the square root of 2, 1 plus BC over square root of 2, one minus plus BD over square root of 2, 1 plus minus BD over square root of 2, 1 minus. And now we group terms together. And so we get AC plus AD over the square root of 2 times 0 plus AC minus AD over the square root of 2 times 0 minus plus BC plus BD over square root of 2, 1 plus, and then finally plus BC minus BD over square root of 2 times 1 minus. And when we compare this to the left hand side, we get AC plus AD is equal to 1, and that's what we get by taking this term into the 0 plus term here and comparing it to this 0 plus term. We have square root of 2 in the bottom in both cases, so just AC plus AD must be equal to 1. There's no 0 minus term up here, so AC minus AD must be 0. And likewise, there is no 1 plus term up here, so BC plus BD must be equal to 0. And BC minus BD, since there is a 1 minus term, BC minus BD must be 1. BC minus BD is equal to 1. So when we look at this, we see that, let's take for instance the second equation. It would imply that AC is equal to AD. And of course A cannot be 0, because if A were 0, it would make this equation impossible. So since A is not equal to 0, it's okay for us in this equation to cancel A on both sides, and we get C is equal to D. Now, if C is equal to D, we come over here to this equation, and we could substitute D for C, and we would get BD minus BD is 1, but of course BD minus BD must be 0. So these equations are contradictory. This is not possible. And so once again, we conclude the state is entangled. But you see that we had to work a lot harder to come to that same conclusion in this case, because we did not pick a very convenient basis for the second qubit of the 2-qubit system. So this is just a word of advice for the future. When you look at a multiple qubit system and you're trying to determine if it's entangled or not, it would probably be it might pay off to think carefully about which basis you want to use for each qubit in the multiple qubit state. So that is our discussion of entangled 2-qubit states. And now let's look at entangled multiple qubit states. And in this case, I believe I'll just stick with the example in your book, which is example 3.2.3. So we have the state we're going to call C, which is defined in this way: 1/2. This is a 4-qubit state. It'll be 1/2 of 0, 0, 0, 0 plus 1/2 of 0, 1, 0, 1 plus 1/2 of 1, 0, 1, 0 plus 1/2 of 1, 1, 1, 1. Now, as your book says, if you're asked about entanglement and and that's all that is given, is that you're just asked if a state is entangled or not, then the assumption is that you are going to decompose this into the tensor product of n qubits. In other words, we'll consider one basis for each qubit present. So just to make sure that this is clear, so we would say 1/2 of 0, 0, 0, 0 plus 1/2 of 0, 1, 0, 1 is 1/2 of 1, 0, 1, 0 plus 1/2 of 1, 1, 1, 1 equals, and again, this is what we would check if we were just asked, is this entangled? Let's then the way we would, if that was the question and no more information was given, then what we would do is the following. We would say A 0 plus B 1 tensor product with C 0 plus D 1 tensor product with E 0 plus F 1 tensor product with G 0 plus H 1. And we see that on the right hand side we would we don't have to expand out everything, actually. We can see this pretty quickly in the following way. Notice that we must have, I'll start with the expansion and then show you how this goes. So one thing we would get is A, C, E, G, 0, 0, 0, 0. And then we would get A, C, E, H, 0, 0, 0, 1, plus A, C, F, G, 0, 0, 1, 0, plus A, C, F, H, 0, 0, 1, 1. And so on. And what we notice is that if you went ahead and wrote out all of the terms, all of the 16 terms that you would have, so I'll just say plus dot dot dot, we notice the following. On the left hand side, there are only two terms that begin with 0, and that is the first two, in fact. 1/2 0, 0, 0, 0 plus 1/2 0, 1, 0, 1. Now on the right hand side, all the terms that begin with 0 must have this A coefficient. So for instance here, ACEG, ACEH, ACFG, ACFH, and there would be others as well. But the only, what we can say is the following. Let me as I was saying, what we can say is the following. ACEG must be equal to 1/2. Now the coefficient for 0, 1, 0, 1, well, by looking at the right hand side, that must be A is for 0. The first one to be 0 means A. The second term to be 1 means D, so we have A, D, and then the third qubit is 0, so that's E, and the fourth qubit is 1, so that's H. So that must be 1/2. And now let's go ahead and look at these. 1, 0, 1, 0. Okay, if the first qubit is 1, that means B. So B. The second qubit is 0, so that's C. The third qubit is 1, so that is F. And the fourth qubit is 0, so that is H. So BCFH is 1, and then finally 1, 1, 1, 1 is B, D, F, H. So these of the 16 terms that we would obtain, these 4 must be equal to 1, but all of the others must be equal to 0. So for instance, AC, EH is equal to 0. ACFG equals 0. ACFH is equal to 0. AD, well, let's put that in the next column. AD EG AD FG ADFH, those are all equal to 0. BC FG equals 0. BC EG equals 0. BC EH equals 0. And the final column here would be BD. So BD EG is 0. BD EH is 0. And finally BD FG is equal to 0. So now if we look a little more carefully, notice right away we can see that this is impossible, because if we look at these two equations right here, these two equations have AC in common. And so, in other words, we could regard this first equation as being AC times EG is 1/2, and that shows that AC cannot possibly be 0. But this next equation says AC times EH is equal to 0, so that means that EH must be 0. But now we come up here, and if EH is 0, then this equation right here becomes impossible. So it doesn't take long to see that writing this state as a tensor product in this way is impossible. However, as your book points out, we can pose a question of entanglement in a different sort of way. And so if we're asked for entanglement with regard to a system decomposition consisting of a subsystem of the first and third qubit and a subsystem consisting of the second and fourth qubit, okay, let's see how that goes. So we'll say, on the other hand, is this entangled? Is this same state entangled with respect to a decomposition consisting of a subsystem of the first and third qubit and a subsystem consisting of the second and fourth qubits. Okay, so when we ask the question in this form, well, first of all, what do we mean? Okay, well, again, we start off, okay, we have C is equal to 1/2 0 0 0 0 plus 1/2 of 0 1 0 1 plus 1/2 of 1 0 1 0 plus 1/2 of 1 1 1 1. Okay. And now again, we want to see if this can be written as a tensor product, but it's now not. We're not going to use a tensor product where it's decomposed into all 4 qubits, but we're going to look into subsystems containing the first and third qubit. One subsystem will have the first and third qubits, and the other one will have the second and fourth. Now, let's think about this. When we have subsystems that are just 1 qubit, then the basis for that subsystem is just consists only of 2 states, a superposition of 2 states. But when we have a subsystem with 2 qubits in it, then the basis must have 4 states. In other words, what I'm saying is something like this. Okay, for the subsystem containing the first and third qubits, we would have something like A and then 0 1 0 3. And I'm putting those subscripts to help us keep track of where these will end up in our final expression. So plus B times 0 1 1 3 plus C times 1 1 0 3 plus D times 1 1 1 3. Now, again, these 4 2-qubit states form a basis for the subsystem consisting of the first and third qubits. Just like up here, you see this is a basis for the first qubit in the expression. This is a basis for the second. This is a basis for the third. This is a basis for the fourth, because we were decomposing this into 4 1-qubit systems. But here we're decomposing, or trying to decompose, into 2 2-qubit systems. So for the 2-qubit system consisting of the first and third qubits, this will be the basis. And then for the subsystem consisting of the second and fourth, we'll have something similar but different coefficients. So we'll have E 0 0 plus F 0 1 plus G 1 0 plus H 1 1. And now we want to put our subscripts 2 4 2 4 2 4 2 and 4. Now, let's see what happens when we take the tensor product on the right hand side. We will get the first term coming out, AE term, will be 0 0. Oh, maybe I should go ahead and spell this out. Okay, so this will be AE 0 0 0 0 plus AF. Now keep in mind that this term gives an A in the first, gives a 0 in the first position, and then this gives the 0 in the second position. This gives the 0 in the third position, and then this gives the 1 in the fourth position. So we have AF 0001. The next one, AG, will be 0 1 0 0. Again, 0 1 0 0, and then plus AH 0 1 0 1. I encourage you to try to go ahead and write out the rest of this for yourselves, and then we'll look at it all together. Now, continuing, the next one will be BE, and then BF, BG, BH, and for BE we have 0010, 0010. For BF we have 0011. BG is 0110, and BH will be 0111. The next set of terms will be CE, CF, CG, CH, and for CE we have 1000. For CF we will have 1001. For CG 1100, and for CH 1101. And then finally DE, DF, DG, DH. DE will be 1010. DF will give us 1011. DG will give us 1110. And finally DH will be 1111. And now, as usual, we compare the left-hand side with the right-hand side, and we conclude that AE must be equal to 1/2. And let's see, the 0101 term is AH. AH equals 1/2. 1010 down here below is DE. DE equals 1/2. And finally, the 1111 term is DH. DH equals 1/2. So we conclude that of these 16 coefficients that we have here, these 4 must be equal, all equal to 1/2, and all the others must be 0. So to make sure that's clear, so AF equals AG equals 0 in the first line, and everything in the second line, all the terms beginning with B are 0. So BE equals BF equals BG equals BH equals 0. That's in the second line. And the third line, everything beginning with C is also 0. So CE equals CF equals CG equals CH equals 0. And then in the last line, we have we already have DE is equal to 1/2, DH is equal to 1/2, but DF and DG are 0. So DF equals DG equals 0. And now we ask ourselves, does this lead to a contradiction as before? But I believe that the answer is no, because, for instance, if F and G and B and C are all 0, notice that would make all of these equations true. Since F and G are 0, those two would be true. And since B is equal to 0, all of these would be true. Since C is equal to 0, all of these would be true. Down here, since F and G were 0, that would be true. And yet, none of these equations would necessarily be false as a result of this assumption. So if we choose F equals G equals B equals C equals 0, and A equals E equals D equals H equals 1 over square root of 2, then all these equations are true. So, with respect to this decomposition, C is not entangled. And let's just for the sake of completeness, let's write this down, and I think it will be a little easier to see then. Remember that C is 1/2 of 0, 0, 0, 0 plus 1/2 of 0, 1, 0, 1 plus 1/2 of 1, 0, 1, 0 plus 1/2 of 1, 1, 1, 1 and according to the work we've just done, we see that that is equal to, now remember, A is 1 over square root of 2, so we have 1 over square root of 2 0, 1, 0, 3. B is equal to 0, C is 0, but D is 1 over square root of 2. So plus 1 over square root of 2, 1, 1, 1, 3. Tensor product with E is 1 over square root of 2, so we have 1 over square root of 2, 0, 2, 0, 4. F and G are both 0, but H is 1 over square root of 2, plus 1 over square root of 2, 1, 2, 1, 4. And once you write it out like that, I think it's easy to see that this is true, because the tensor product of the first with the first would be 0, 0, 0, 0, and we'll have 1 over square root of 2 times 1 over square root of 2 is 1/2. So that takes care of this term on the left. and then this term tensor product with that one would give 0, 1, 0, 1, which is this. This term with this would give 1, 0, 1, 0, which is that one, and then this term with this would be 1, 1, 1, 1. So this shows that when you're talking about, of course, when you're talking about just a 2-qubit state, it can only be decomposed into 2 1-qubit states. But when you're talking about multiple qubits, it is important. If the book does not specify what they mean by entanglement, then then you should assume that for an n-qubit state, we are talking about decomposition into n 1-qubit states. But if as we have just seen in this example, just because something might be entangled with respect to n 1-qubit states, notice that C was entangled with respect to the 4 1-qubit states. It was entangled, but with respect to decomposition in terms of these 2 2-qubit states, or 2 2-qubit systems, one system containing qubits 1 and 3, and the other system containing qubits 2 and 4, with respect to that decomposition, this is not entangled. So this is an important concept to remember. Well, since the lecture so far has taken a bit longer than I had anticipated, I think we will save our third topic, this measurement of 1 qubit of a 2-qubit state. We'll save that for lecture 10 and go straight to the problems now. So the first 2 problems are as shown here. The first one says circle, and you should circle all the states that are not entangled. And we have 1/2 0 0 plus 1/2 0 1 plus 1/2 1 0 plus 1/2 1 1. Here for B, 1/2 0 0 minus 1/2 0 1 plus 1/2 1 0 plus 1/2 1 1. In C, we have minus 1/2 0 0 minus 1/2 0 1 plus 1/2 1 0 plus 1/2 1 1. And finally in D, minus 1/2 0 0 plus 1/2 0 1 minus 1/2 1 0 plus 1/2 1 1. And then again in 2, we circle all the states that are not entangled. In A, we have 1/2 plus plus, plus 1/2 plus minus, plus 1/2 minus plus, plus 1/2 minus minus. In B, we have 1/2 plus plus, minus 1/2 plus minus, plus 1/2 minus plus, plus 1/2 minus minus. In C, we have minus 1/2 plus plus, minus 1/2 plus minus, plus 1/2 minus plus, plus 1/2 minus minus. And finally in D, minus 1/2 plus plus, plus 1/2 plus minus, minus 1/2 minus plus, plus 1/2 minus minus. And then in class, we will have one more question on entanglement, and in fact, I'll give you a hint if you want to be thinking about it. We will have entanglement of a 3-qubit state, and so you should be maybe thinking about that, but we'll be doing it in class, and of course if you have a question, you'll be welcome to ask. So and then we will save any problems for that last topic until the next lecture. So that concludes lecture 9, and good luck.